Alright, so hello and welcome to this video tutorial for RC Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 4 here, which is asking us to determine the resultant force and specify where it acts on the beam measured from A. Now, as I'll always suggest with these problems, I like to approach them basically by converting distributed loads into point loads. So we could kind of decompartmentalize this problem. We could say we have one kind of distributed load here, which takes this right angle triangle shape, and we have another kind of distributed load here, which also takes a right angle triangle shape. Let's first concern ourselves with the position of these point loads, then, if we're to kind of convert both of these distributed loads into point loads. So if you didn't know already, the point load, or at least the kind of point load conversion of one of these distributed loads, will act down from the centroid of the shape. Now, for a right angle triangle like this, basically the centroid is 1/3 of the length of the triangle, so 1/3 of the length of the triangle away from the utmost altitude of the triangle. So in this case, our distributed load on the left here, we can represent like so, and we can say then that this length here takes a value of 1 meter, since 1 is 1/3 of 3. And in the case of this point load on the right here, we can say that this length here is 2 meters from A, okay, since 2 is 1/3 of 6. Let's move on to solve for the magnitudes of these point loads here now. So I'm going to label this one on the left F1 and this one on the left F2. Let's work out F1 first. So if you don't know already, we can determine the magnitude of this point load by calculating for the area of this distributed load here. The area of a triangle is a half times base times height, so we've got a half times 3 times 6 here, which gives 9 kilonewtons. And for F2, again, we could do the same thing. We can say a half times base, which in this case is 6 times height again, which is 6. A half times 6 times 6, that's 3 times 6, that's 18 kilonewtons. Now, we want to determine two things about this resultant force, right? We want to determine its magnitude and its position. We can determine its magnitude off the bat. We can say that the resultant force here is the sum of F1 and F2. It's 27 kilonewtons. We can then move on to calculate for the position of FR. Let's say that FR roughly sits around here, and we can describe the distance between A and FR as x. So this little length here we can describe as x. And the idea basically is that the moment about A produced by the resultant force is equal to the sum of the moments produced about A by forces F1 and F2. Okay, so what that looks like is we can say 27x is equal to the sum of the moments produced by F1 and F2. So the moment produced by F1 here is going to be, let's call it -1. -1 since it's acting anti-clockwise, and we're taking anti-clockwise as the negative direction here. So -1 meter times 9 kilonewtons plus 2 times 18. We can simplify our right-hand side to 27. And so we're saying that 27x is equal to 27. Almost by inspection, then we can say x is equal to 1. Okay, so this length here is equal to 1. And these are our solutions. So if you have any questions or comments about this problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.